Professor Katerina Lipka from DESY has presented a review that's showing that the importance of studies of T-quark. Even though T-quark was discovered more than 30 years ago, up to now it is one of the hot topics in particle physics. Why this situation remains like this?
So indeed, the top quark is the most massive fermion we know today, as you know, and being the most heavy particle. I mean, heavy we cannot speak because it is not object of
That was
much
the
of this
discussion
we can measure. So the quark is the concept of the model, and its mass is the model parameter. So the model which we use to describe our world is a standard model of particle physics. It's a quantum field theory, and the top quark mass is the parameter of it. But though it's very important in the QCD, the quantum chromodynamics, which describes the interaction between quarks and the gluons, which is a strong force description which we know, it still plays a role also in the electroweak sector of the standard model. So the mass of the top quark is binded together to the mass of the Higgs boson and the W boson. So by measuring the mass of the top quark very precisely, we can study not only the quantum chromodynamics, because it's a fundamental parameter of it, but also perform a very important self-consistency test of the standard model. Together with a strong coupling constant, the top quark mass influences the prediction for the Higgs quadric coupling, which, for example, is important for the interpretation of the stability or instability of our electroweak vacuum and though our universe. So for the moment, its prediction of this quadric coupling of the Higgs boson as a function of the energy or the temperature in the universe depends very much on the value of the top quark mass and its precision. Improving the precision of the top quark mass, we would also improve the precision in this prediction for the stability of the electroweak vacuum. It is still a very, very high challenge to know the top quark mass very precisely, but again, it's not a particle which we can reconstruct experimentally.
No, obviously.
It decays into the W boson and the B quark, which we reconstruct by the missing energy, by the B-tagged jets, by the lepton in the final state, which is an experimental challenge. So that's why we cannot just probe directly the top quark mass, but we have to reconstruct the top quark cross-section, which is unobservable, which we measure with a certain precision, and then we confront it to the theory prediction, which also has an uncertainty, and then extract, for example, the top quark mass or other parameters of the top quark. And we measure the cross-section, we measure the mass, we measure the top quark width. It's a huge, very rich program at the LHC to study the top quark. And my part of the field is to study the top quark in its aspects related to the quantum chromodynamics.
I see.
It's
And
relation to the gluon distribution, to the strong coupling constant.
And from which of the experiments you suppose the most new information about this top quark mass?
So we are working together, Atlas and CMS experiments, because LHC is of course a top quark factory, producing billions and zillions of top quarks. So at the moment, the LHC is a facility to measure the top quark properties precisely. We need significant impact from and also the input from our theory colleagues to provide the calculations at highest order perturbative theories, and also to be able to describe the non-perturbative parameters, which are also related to the top quark production at the LHC, because we are colliding the protons. So, and also non-perturbative effects like fragmentation, parton distribution functions also enter the calculation and define the precision of these calculations. And then we'll try to combine the results. I mean, LHC is already doing that. There is a top LHC working group where the results on the top quark mass and width and cross-sections are combined. So that gives you the ultimate precision. But of course, since the LHC is a proton machine, we will always be limited by the understanding of the proton structure and the correlations between the proton structure and the strong coupling and the top quark mass. We're working, of course, on developing novel methods to decorrelate all of these. But of course, the ultimate precision, if I may speak about far future, or hopefully maybe not so far, would be the linear collider, which we all hope for, where in E plus and minus collisions we can measure the top quark production with tremendous precision, which unfortunately we cannot reach at the LHC.
So it means that this problem of top quark mass remains as one of the key point of weakness even for the future machines, yeah, obviously.
Can be, because I mean, look, at the moment we didn't find any new resonances, any signs in the direct searches for the new physics. But if we are talking about the top quark as a probe for the new physics, it is a very nice instrument to really go to the very, very high precision in the standard model, so that we, by increasing the precision of the standard model, we can find the hints to the new physics, basically.
Well, thank you very much.
Thank you.